Okay, we'll start the class. This is the TA session for Structural Analysis 1 taught by Professor Amit Shaw. I'm Trisha Chakraborty, one of the teaching assistants. I am a PhD student at the Indian Institute of Science, Bangalore. Now, there are two broad branches of structural engineering. One is analysis. Analysis is basically the forward problem. So, here we will be structural In structural analysis, we will be given the structural dimensions, the boundary conditions, and the applied loads. For example, we have a beam. We know the cross section of the beam, the material, and we know what kind of boundary conditions are there and what kind of loads are applied. And we want to find out the response induced in the structure. Responses are mainly of two natures. One is the force related response, and another is the displacement related. So, forces we need to find the force in the along the beam, and the as a result the stress developing in the beam. So that is one part, and the other part is the displacement or the deflection at each point of the beam. This is just an example. It need not be a beam, it could be any structural element. So analysis is the forward problem. We would be given the structure and we have to find out the response. And design is the inverse problem. In design, what we do is we will be given we have suppose we have to design a beam. We don't know the dimensions of the beam. We are allowed to choose the cross section. We are allowed to choose the material. We cannot choose everything. We will have certain limitations. That suppose we have five options of concrete yield stress, we have to choose between them. So we would be given the loads that need to be withstood by the structure. So suppose we know that this amount of force is about to come on a column or a beam, and there will be some things also we would know that we are likely to know the boundary conditions already, because if we are designing a structural element for a larger structure, we would know the boundary conditions whether they are fixed or hinged. I will go into them later today. So those will be given, and then there will be certain criteria. On, for example, on maximum deflection, there are these are serviceability criteria that the mid generally, if I have a beam which has loading in the downward direction, it will it will deform in such a way that the midpoint has the maximum deflection. So there will be a maximum deflection criteria on that, that I cannot exceed that. So then we have to find the optimum size of the structural elements. Design. So the two broad branches are analysis and design, and this course is a course on analysis, structural analysis. It is one of the most important courses in civil engineering. In an undergraduate curriculum, analysis is one of the most basic courses, and design you will probably get to it next year. There are, in India or in the world, there are two main materials that are used, concrete and steel. So there will be a course on concrete design next year and one on steel design. So why do we need structure analysis? As I said, it is basically performed prior to the design stage. So what this means is that for the design, we need to know the forces that the structure needs to withstand. Now this is basically a cycle kind of thing. So suppose I have to design a building, just because it is very easy to visualize. What do we actually know about? We know the soil uh, criteria, that what wherever we are designing, we know the details of the soil. We know the requirements of we know the basic architectural requirements. We will be given that these number of rooms we can have, these many floors. And the about the forces, we have some input, like we there are in the Indian standard codes, there are IS codes. There are some standards of loading given, that for a residential building I have to take a live load of 2 kilonewton per meter square. For a industrial building, we have to take 3 kilonewton per meter square. So I know the live load that I have to take, I know the dead load that I have to take. And then considering the region it is built in and the soil criteria, we have some earthquake loadings and wind loading patterns that we have to take. So these are the broad force loading patterns that we have. But now this cannot directly be used in design, because when we design, we have to do it element wise. We have to design each beam, each slab, each column, then each foundation. So we need the forces developing in each of those elements. So what we do is, we would suppose first we would propose a framework of beams and columns. Then we will take the broad loading that we need know from the IS codes. Then we have to perform structural analysis in each of the elements to find out the forces that are going to develop in each of the elements at the different cross sections and all. And then we have to go into design with using these as input. So basically, structural analysis in the wide process of design, which is the ultimate goal of structural engineering, you can say, it provides the internal forces and stresses corresponding to the design loads. And these not designed loads, it will be design loads. And these design loads are what we get from the Indian codes. And the structure analysis will typically account for the materials used, applied loads, and geometry of the structured object. Now these applied loads, geometry of the structured object, these we generally get from outside sources. Geometry we generally get from an architectural design. The architectural drawing will have certain details that we have to work with. Yes, and the materials used, we have to take a call as a civil engineer. We will have we will have to take a call that what material we have to use. Suppose it will be already mentioned that when once a structural engineer gets an architectural drawing to design, mostly the material will be mentioned, that whether it is concrete, what grade of concrete should be used. But sometimes for specialized structures, we might have to go for a very high grade concrete, or sometimes steel structures. So these structural the processes, we have to first we are given a drawing. Then we have to study the loadings that we have to take from the IS codes. We have to perform a structural analysis, and then we design it from bottom to top, meaning each element. And then each element the so the load transfer mechanism in a building typically is the load that we the building furniture, the people apply is on the slabs, then that is transferred to the beams. The beams are what the horizontal elements. Then they are transferred to the columns, because these days, like generally, walls are not load bearing elements, so the entire vertical load is taken by the columns. The columns take it down to the foundation, which is below the soil, and then the load is transferred to the soil. So basically, what so the load transfer mechanism is very important to understand when we are designing something, and that is also important in the structure analysis process, because that is from where we get the boundary conditions. So we go into the types of internal forces induced in a structure. The first is bending moment. It is moment that occurs when an external force is applied to the element, causing it to bend. So it is very easy to visualize. If this is a beam, if you apply a force here, it will bend in a profile like this. If they are, suppose they are supported at the two ends, and you apply a downward force or upward force at the midpoint, it will have a bending like this or this. So the moment that is developed at each cross section is the bending moment. So we study these forces according to cross section. At one cross section, we assume there is a mostly a uniform bending moment developed. The next is shear force. Shear force is force that acts parallel to the cross section of a structural element when an external force is applied. And again, this bending moment and shear force are both generated due to forces that are parallel to the cross section. So suppose this is a beam, then this is its cross section. So any kind of force that is applied parallel to the cross section, that is in this direction, it will give rise to both a bending moment and a shear force. Shear force is the force and bending moment is the moment. And torsional moment and axial force are they are basically generated due to a force that is perpendicular to the cross section, so in this direction. You can imagine axial force is force that acts in the direction of the axis of the body. This is the axis of the body. So if I am applying a compression or a tension force here, the force that will be generated inside this is the axial force. And the torsional moment is And torsional moment is moment produced by a twisting force applied to the body along the transverse axis. So this is torsion. If this is a beam, this is the cross section you are seeing, then bending moment is the when if I apply a force like this, it will bend like this. The moment generated is the bending force and bending moment. And if I apply a force like this is the torsional moment. So there are two types of forces, axial force and shear force, two types of moment, bending moment and torsional moment. These two are a pair. The first two are a pair because the force is applied parallel to the cross section, and these two are a pair because the moment force is applied perpendicular to the cross section. This is how you can visualize it. This is tension, and tension is when both the forces are pulling away from the body, so it will have an elongating effect. And compression, tension and compression together make up the axial forces. For compression, it will be the both these four arrows will be directed inward, so it will be a force like this. Shear forces, see, this is the cross section. Okay, this is the cross section. So you can see that in tension the force is perpendicular to the cross section, and for shear the force is parallel to the cross section, and for bending also the force is parallel to the cross section, and this is the bending moment. And for torsional moment, this is the moment that's being generated. But you know, by the corkscrew rule that we studied in class 11 and 12, that any moment has the sense of the moment is basically perpendicular to the plane in which it is occurring. So this is the moment that I'm applying, and the sense of the moment is along this, so it is the same as the similar to the axial force. Now okay, we for firstly, when we are looking at any real world structural elements, they are very complicated. But we have to, as civil engineers, we as engineers, the entire purpose of engineering is to simplify and approximate real world phenomena, so that we can reach a logical conclusion about them. So first, in structural analysis, we have some idealized types of elements in the 2D plane. Nothing around us is actually 2D, but there are some approximations that we can make. That, for example, truss element is an element in the 2D plane that transfers only axial force, so it can only undergo tension or compression. It is also called a two force member. But actually, in if you have seen bridges, wait, No, I don't have a picture here, but there's a common most bridges like steel bridges above, for example, the Howrah Bridge. It is made of trusses, so it is not actually 2D. But we have seen, like people researchers have seen that if even if we approximate all the elements as 2D elements, we are getting a proper result. So maybe there will be some error involved, but if that is acceptable for us, it is in making the process easier, the process of design analysis much easier, so we can accept that, we can accept certain approximations. So the truss, the one type is truss element that transfers only axial force. The beam element transfers only shear force and bending moment, and the frame element transfers all three. So the truss, so truss element is something like this that will only undergo tension and compression. The beam element is the most commonly visualized element when we are talking about structural analysis. The first element that comes to our mind is a beam element that undergoes bending and shear. So see, it's, you cannot say that there is a beam element and a frame element and a truss element. They won't look different. We will treat them as a truss element if we know that only a tension and compression is can possibly be generated in this. And a beam element, suppose there is one element part of a frame which only has loading along the cross section, so we know that only shear force and bending moment will generate in that cross section, so we can treat it as a beam element. And if an axial force comes, it we will treat it as a frame element. So they don't look different, it is our treatment depending on the kind of forces that are developing there. And then the next, we have looked at the type of element, and the next part is the types of support in the 2D plane. Yeah. So there are several kinds of support, but these three are the most common. Roller support. Roller support is represented typically by a triangle and two balls, or it is also represented as a single ball. You, since these questions in generally in questions you will be given a diagram, so you have to identify which is which. So this is a roller support. It can also be just a ball. It restricts displacement only in the direction perpendicular to it. So it means that if you try to push this down, if you apply any force, this force, there will be a force generated here. So in the vertical direction there is going to be no displacement allowed, but if you pull it like this, if you apply a axial force on this will move, because it will provide no resistance in the horizontal direction. And similarly, the third type of movement is the, see, okay, I should have said this before. In a 2D plane, the three kinds of displacement that we are concerned with are the horizontal displacement, the vertical displacement, and this moment. Okay, so this moment is basically in the z, along the z direction. The sense is in the z direction, it looks like this. So this roller support restricts here displacement in the y direction, but it allows displacement in the x direction and rotation along the z direction. And hinge support restricts displacement in both directions, so there will be no displacement in the x direction or the y direction, but it is free to rotate. And a fixed support restricts displacement in both direction and out of plane moment, so this is, it won't move here this way, it won't move this way, and it won't even rotate. And see, so one thing we can say is that every kind of, like, the force has a corresponding displacement component to it. So if a support restricts displacement in a particular direction, it means the force along that direction at the support will be unknown. So here, since no vertical displacement is allowed, there will be a vertical force developed here, a reaction force that is unknown to us. So at any point corresponding to the three types of movement, either the force is known or the displacement is known. So in roller support, the displacement in the y direction is known, so the reaction force in the y direction is unknown, that we have to find out. And the displacement in the x direction and the rotation in the z direction is not known, but we know that there is no force in the x direction and there is no rotational moment developed at the support. And it is like here, since all three modes of displacement or rotation is restricted, all the three reaction forces are unknown to us. And here we have two unknown reactions, rax and ray are unknown, but since the rotation is free, there is no moment developed here. Structural indeterminacy, structures that cannot be analyzed using basically to, why these three equations are also So these, since there are three kinds of motion or force allowed, there are three equilibrium equations that we have in the 2D plane. We know that for a body to be in equilibrium, the summation of forces along the x direction should be zero, the summation of forces on the y direction should be zero, and the summation of the moments about the z axis should be zero. These are the three basic equations that we have if any body is under equilibrium. And when we are designing something or when we are analyzing something, we are obviously considering that it is at equilibrium. Because see, suppose you are dropping something, suppose you let something drop, it has no resistance, it is just dropping through the air, there will be no stress or force generated in the structure. But when it hits the ground, it has to stop, then that is when the force and the stresses come. So unless something has a resistance, no forces or stresses will be generated. So we are not concerned about that. That is a separate area called dynamics. We are working with statics, where all the bodies are under equilibrium. So the three basic equations in the 2D plane we already have. Now suppose there is a structure that cannot be analyzed using statics or equations of equilibrium. That means there are more unknowns than there are equations. Suppose there is a beam with two hinge supports. At each hinge support, I have two unknowns, the x direction and y direction force. So if a beam has two hinge, suppose there are four unknowns, but there will be only three equations because it is in the 2D plane. So that is a 1 degree indeterminate structure. If you have two fixed supports on the two ends, then there are six unknowns and three equations. So it is a 3 degree indeterminate system. Now, to solve those, they require other material properties to be solved. We will look into that later. I think the last 4 lectures work with statically indeterminate systems, and so we are starting with the solving part. We will start with determinate systems. The degree of indeterminacy is the number of unknown reactions minus the number of equations of equilibrium, as I said. And in the 2D plane, this quantity is always fixed. The number of equations of equilibrium in the 2D plane is always 3. So we have to just see the number of unknown reactions, and subtract 3 from it to get the degree of indeterminacy. This is also called the degree of static indeterminacy, since we are doing static analysis. Now the indeterminacy are split into two parts: external indeterminacy and internal indeterminacy. External indeterminacy is the total number of independent support reactions minus the total number of available equations of static equilibrium. Internal indeterminacy is total number of internal reactions minus available equations of equilibrium. This is a little difficult to gauge. So the degree of structural indeterminacy is the one that we saw in the previous slide. That is the external indeterminacy plus the internal indeterminacy. So to find, basically what we do is, if we are given a structure and we are asked to find these three quantities, we find the external, and then we find the total degree, and we subtract this quantity from this to get the degree of internal indeterminacy. Examples: this is called a cantilever beam. A cantilever beam has a fixed support at one end, and the other end is free. Free means it is in the 2D plane. It is free to displace in the x direction, in the y direction. It is free to rotate, and the fixed support is the opposite of that. Everything is completely constrained. So this is a cantilever beam under this kind of loading. So this loading, if you see something represented like this, or a series of arrows pointing downwards, it is called a uniformly distributed load, and it is expressed as a quantity per meter. So it is probably like, since it is a distributed force, suppose the total force here is 10 kilonewton and the length is 2 meter, then the distributed load will be 5 kilonewton per meter. That is how it is expressed. So this is a cantilever beam under uniform loading. In uniformly distributed loading, it is a very common uh, a very common problem. So the degree of indeterminacy here, what will be, because so we will look at the number of support reactions. The number of support reaction is, at this point there will be a force in the x direction, a force in the y direction, and a moment. And here there will be no reaction. So there are three total support reactions, and we know that we have three equations. So this is a determinate system. So we can solve the forces and display. We can solve the forces without looking at any material property. It doesn't matter what the material is, we will always get the same answer. This is a slightly complicated problem. It has a fixed support, and it has a roller support at this end, and it has a uniform distributed loading up to a certain point. This is like, we are not going into the analysis right now, but that will the analysis, the distribution of this load will of course affect the force pattern and all. So here we have three reaction forces at A, in the x direction, in the y direction, and moment in the z direction. And we have at C, we have only one support reaction in the y direction, because other two modes of displacements are free. So we have four support reactions and three equilibrium equations. So the degree of indeterminacy is 4 minus 3 1. This is a frame, these are beams. Okay, and another thing I have to mention is that, see, it is not explicitly mentioned it is a beam, that these two are beams, so we are considering axial displacement or axial force as a parameter. But if it is actually a beam, what we studied about beam elements here is, beam element transfers only shear force and bending moment. So you can probably, we understand that in here that we are looking at three modes of displacement: x, y, and z rotation. So this x displacement or force in the x direction is basically an axial force. So if we are told that this is a beam element, then that mode is completely eliminated, we are not going to consider that. So the, so we basically, then we will have two equilibrium equations, that summation of Fy will be 0 and summation of moment about the z direction will be 0. And we have two modes of and we have two support reactions, one in the y direction and one will be a moment along the z axis. So anyway, the result will be, it is still indeterminate, it is still a determinate system. But if it is given as a beam element, do not consider the displacement along the x axis. Similarly in this, if we eliminate the x direction force and force and displacements, then there will be two unknown forces here and there will be one unknown force here, and we have two equations here. Because see, if it is a beam element, we have only two equilibrium equations, because summation of fx equal to 0 is by default by default satisfied there, because if it is a beam element there is no axial force, so summation of fx will always be 0 and it is a redundant equation. So we have basically two equations: summation of fy will be 0 and the summation of rotation will be 0 about the out of the plane or into the plane. So we will have two equations and we have three unknowns, two here and one here. So the degree of indeterminacy remains 1. So, but so since it was not mentioned it is a beam element, we just look at it and assume it's a beam element, because as you do, as you get into this course, looking at this will obviously look like a beam. But do not assume that if it is not mentioned, you have to consider the axial part as well. Now this is a frame, and frames have all three types of all three modes. This frame has a fixed support here and a fixed support here. So there are three unknowns here: fx, fy is, sorry, a force in reaction in the horizontal direction, in the vertical direction, and a moment here, and similarly in this. So there are six unknowns and the number of equation remains 3. Just because it's a frame doesn't mean there are more equations of equilibrium available. So the degree of indeterminacy will be 3 plus 3, 6 minus 3, that will be 3. And this is another frame, and these are hinge support. Hinge supports look like, are represented like this, or sometimes in, you can, like, if there are no balls involved here, it is a hinge support, otherwise it's a roller support. So at a hinge support, these 2 points are free to rotate, but they cannot displace in this direction or this direction. So there are two unknown forces here, two unknown forces here. So four support reactions unknown and three equations. So the degree of indeterminacy is 1 here. Okay, any questions so far? Okay, I'll go on to the next part. Now, internal forces and beams. We have looked at the total, there are four types of internal forces: shear force, bending moment, axial force, torsional moment. But since in a beam, we are not considering the axial force, so torsional moment is also not applicable here. So we have two types of internal forces: shear force and bending moment. And suppose this is a beam element and I apply a transverse load P here. This is a transverse load because the force is in along the direction of the cross section. So what the shear force, the way we study shear force is, or bending moment is, we have to take a cross section. This is a cross section at a certain, suppose at a distance x from the fixed support. So at this cross section, I will ask you to find out the shear force and the bending moment. So the basically the meaning will be, we have to split, we have to imagine that there is a split at this section. This part is the left portion, this is the right portion. The boundary conditions and the forces will remain in its own places. Then a pair of, since this is in equilibrium, if at a section there is a shear force, the net force at that section has to be zero. So there is a pair of shear force developed here. At this point, if it is in downward direction, at this point it will be in upward direction. I don't know from before whether it's down or up. All I know is that the pair of shear forces will be developed at the left surface and the right surface. If we are imagining this is a section, I've just split it. There will be one shear force here, one shear force here, and they will be in opposite directions, balancing each other out. And similarly, the bending moment also will be a pair of moment in opposite directions, opposite senses. So this on the left surface has shown a clockwise moment, and the right we have shown an anti-clockwise moment, and the magnitudes are same. And again, I say that before we have analyzed it, we do not know that this is clockwise, this is anti-clockwise. We are just assuming. Then after solving, if we have to assume a direction, we have to solve it. And if we get this v as negative, it will mean that we have assumed opposite. That if we get v positive, it means that this side is actually upward and downwards. And if we get the m as positive, this means that this part is clockwise and this is anti-clockwise and this is clockwise. And if we get it negative, we have to just reverse the signs. Now there are the sign convention is very important here. Bending moment. The bending moment, like, see, when we are looking at equilibrium equations, the sign convention is much easier to grasp. It's much easier to visualize. That suppose I'm doing an equation, sigma f y equal to 0, we can take that forces pointing upwards are positive, forces pointing downwards are negative. So we algebraically put all of those, and like when we are summing up all the forces, we will algebraically put them and equate them to 0. And similarly for moment, suppose I am equating the moment, I'm saying that the sigma mz equal to 0, I will, for my convention, I might take that clockwise moment is positive. So while we are writing the equilibrium equation, any clockwise moment we encounter, we will put as plus. Any anti-clockwise moment we will put as minus, and we will equate it to 0. So that sign convention is fairly intuitive. But the bending moment and shear force are tricky sign conventions, because it is a pair of forces, right? It is, you cannot, what will a positive shear force here mean? Why will I call it positive? There is something downwards, something upwards. So we have to standardize it. I'll look at the shear force first. Shear force sign convention is, if on the left surface it is upward and on the right surface it is downward, it is positive shear force, and this is negative shear force. So if this is indeed the actual shear force pattern developed, then this will be a negative shear force. And for bending moment, there will be a pair of moments developed. So if the left moment is in the clockwise direction and the right is in the anti-clockwise direction, we will call it positive bending moment, and this will be negative bending moment. And while these sign conventions, so now it will probably seem confusing if you have not done any problem before, but if you see, once you get the hang of it, it is not difficult to understand. And again, see, a sign convention can never be universal. If I want any day that I'm solving a problem using the reverse sign convention, I'm going to call this positive shear force, I can do that. But if you are solving a problem in an examination, it is better to mention the sign convention that you are using, just to be clear. And another thing to be mentioned here is that, if for positive bending moment that we call as conventionally positive, this profile of bending will be noticed. So you can try that with, like, take a sheet of paper. Imagine a sheet of paper. You are doing on the left side, you are doing a clockwise, giving it a clockwise moment. Here you are giving it anti-clockwise rotation. You will see it will bend in this profile, and this is called a sagging bending moment profile, and this is called a hogging profile. So this is what you can remember it as: sagging is positive, hogging is negative. And you can look at this example. Look at this. Just try to visualize that if you have this fixed and you are putting a force like this, you can clearly imagine it will have a displacement profile like this. And this is a hogging profile. And if you And on the other hand, okay, not this, if it was just a simply supported beam that both the ends are just held up like this, and you put a force here, it will reflect in this profile, so that will be sagging. So you can intuitively understand which one will be positive moment and which is negative bending moment. Now, shear force diagram and bending moment diagram. Again, this is one of the most basic and important parts in your entire civil engineering curriculum undergraduate that you are going to study. And because it will crop up everywhere. When you are doing design, it will come. When you are doing higher types of structure analysis like finite element, everything. This is the very basic thing that you have to understand very clearly right at the beginning. So it is a graphical representation of shear force distribution and bending moment distribution along the length of the beam. So that is what we are concerned about. The beam is a three-dimensional object, right? It has a cross section, so it has a width, it has a depth, and it has a length. But we have seen, like, it is a convention or an approximation taken that the bending moment and shear force distribution along the cross section is taken to be constant, but along the length it will definitely vary. So we represent the beam as a line. We take only its length to be the relevant dimension, and the other two dimensions are kind of ignored. The width and the depth of the beam, the cross section, whether it is circular, whether it is square or rectangular, we are not looking at that right now. The length is all that matters, and we will be given the loading pattern, we will be given the boundary conditions, and I have to see the shear force distribution I will have to come up with a graphical representation so that I can read off the shear force at any particular cross section that I want. By any cross section, this is what is meant, that this is an AA. It is generally expressed by like a pair of letters AA. Suppose I take a cross section here BB. So that is defined by its position along the length. So it can be said that this is at a distance x from the fixed end, or it is at a distance y from the free end. So long as you can locate a point along the beam, this is the cross section we are interested in, and this is the point at which we want to find out the shear force and bending moment. And now for the diagram, what we do is we find, like, we represent the shear force along this line, so that if I ask you that find the shear force at this cross section, you can just see the length of the graph at the what is that called, that y coordinate of the graph at that point. And so you can get it at all the points. I will give you the x to define a cross section. I have to give you the x, and you can just read off the y coordinate from the graph and say this is the shear force at that point. And it is of course drawn along with sign, so that is why the sign is this is the sign convention that we are going to follow. The graph will be, it can be positive and negative at any point. Example, this is a complicated, like, not a very simple problem, because it has a lot of uh, there is a jump or a change in the shear force and bending moment pattern when there is a point load or when there is a boundary condition. So there are a lot of point loads, and point load here, there's a boundary condition here, there's a boundary condition here, then you have applied a moment here. Ba- so there are a lot of jumps and changes in the shear force and bending moment diagrams. So this is just an example of what it looks like. This is, if this is my shear force diagram, I tell you that find the shear force at the midpoint. This is the 3733. So the midpoint is somewhere here. If I tell you find the shear force here, you are just going to come to this point in the diagram, this point, and this is minus 1.8 kilonewton. So this is the shear force at this point, and the bending moment here, it is a straight line in this region. So if you know the point, you can find out the coordinate by basic like similarity of triangle things. So so we want to reach a stage where you are given any beam with any kind of loading pattern and boundary conditions, any kind along its length, and you have to come up with these two diagrams, the shear force diagram and the bending moment diagram, so that you can use it in, you might need to use it in design and all that. And now the units are also, just keep that in mind. We know that force, the unit of force is Newton, but in civil engineering, generally forces are expressed as kilonewton, because in kilonewton the values come a little like manageable, 1.8, 2, 3, and in newton if you write 2000, it's easier to write in kilonewton, so that's what we follow. And bending moment, we know moment is force multiplied by a distance, like if I apply a force here, then the moment at this point will be this force into this length, so the unit is newton meter, and here we use kilonewton meter. So the location, so the along this direction, the x direction has a unit of meters, and for shear force, the y coordinate has a unit of kilonewton, and for bending moment diagram, the y axis has a unit of kilonewton meter. We are going to solve some problems to see how this works. Okay. So first we have to understand the the problem and the various information that we have been given. We know the length, of course, at A. Okay, and we name each point. Each you can understand which points you have to name. Each special point you have to name. So here there is a support. Here there is a support. Name them. Here there is a point load. Here there is a point load. Name them. And there is a uniformly distributed loads between C and D. So we are naming. We are not naming the points in between because if there is nothing special happening in a stretch like this, the nature of the plot is not going to change. You can just find out the shear force and bending moments at the special points and join them. And whether you are joining it by a straight line or a parabola is again something we have to look at. So what do we know about this problem? At A, I know it is a hinge support, so I know there will be a reaction force in the y direction, and there will be a moment reaction uh, about the z axis. At this point, this is a roller support, so there will be a reaction force in the y direction. This is what I know. I'm going to the problem. So the first step is solve the reaction forces. To solve the bending moment and shear force in the entire problem, the first step is always solve the reaction forces. And how do we solve them? We use the equilibrium equations. So sigma Fy will be 0. So what are the forces in the y direction? Ra is an unknown, Rf is an unknown. And suppose I'm assuming, okay, so here the upward forces are written in the on the left side, and the downward forces are written in the right side. So Ra plus Rf, we are just assuming that they are both positive. Ra plus Rf is equal to 5 kilonewton, it is downwards, 10 kilonewton downwards. And what is the force? Okay, so since these this is shown like this means it is in the downward direction. If these were made on the bottom side of the beam, it would mean that the uniform distribution force is in the upward direction. Here it is in the downward direction, which is more conventional. So what is the force due to this? See, this is 3 kilonewton per meter distributed over 4 meters. So the total force here will be 3 into 4 kilonewton. So you have to multiply the magnitude of this w, which is generally written by symbol w into the length over which it is being applied. So Ra plus Rf is 5 plus 3 plus 3 into 4. So Ra plus Rf is 27. I've got one equation. And what is the other equation I have in 2D? If sigma Fx equal to 0 is a redundant equation because there is no axial force. And we know that this hinge support can provide a reaction in the x direction, but that will be 0 because there is no load, so there will be no reaction. And the other is sigma now this f is the is see here the sigma f y 0 means in the y direction. This should technically be written as sigma mz equal to 0 if this is the z axis. So the all the moments, adding all the moments about any point to when if a moment is conserved in a plane, it means that you can pick up any point and you can add the moments due to all the forces and reactions along with sign, and you can equate it to be 0. So here this f represents the point about which we are checking the moment. So let's go from the left side. At this point I have a force ra, and I have assumed it is in the positive direction, upward direction. So, and the length, the lever arm that we call, that is the distance, the perpendicular distance of application of this force to the point about which I am looking at the moment. So it will be Ra into this length, this full length, that is 3 plus 1 plus 4 plus 3 plus 1, that is 12. So Ra into 12 is the moment applied due to this reaction force about the point F. And what is the sense? You can just move your hand and see that if the force is like this, you have the point F here, so you do this and you find that it is in the clockwise direction. So suppose for this I'm assuming clockwise is positive. This is completely up to you, and you're going to get the same answer whatever sense you use as positive. So Ra into F is one moment I've got about F. Now look at the next force, that is 5. So this will be 5. It is applied at a point, applied at this lever arm is bf, that is 9 here. And this is written as minus because if I'm taking this sense as positive, this is an anticlockwise moment that is being applied. This force is applying an anticlockwise moment about the point f. So This is minus 5 into 9. Then look at the, this is important. So when we have a uniformly distributed load, we can assume, like just for when we are taking the moment, we can assume that the entire force that is here, the total force, that is 12 kilonewton, is being applied at the midpoint. If you do the, if you like do an integration of the of the moment applied due to each part of it, you will see that it comes equivalent to, since this is a linearly distributed force, it, if you can, if you take the 12 kilonewton lumped at the midpoint of this zone, you are going to get the an equivalent result. So I'm going to take 12 kilonewton at this point. So this point, suppose the midpoint of C and D is M, then the length will be 1 plus 3 plus 2, right? Because this is 4. So from the midpoint, this will be 2. So 2 plus 3 plus 1, that will be 6. So 12 into 6. And again, this is a negative moment since it is in the anti-clockwise direction. And this is the last force, again anti-clockwise, minus 10 into 1. So basically what we did is, in this equation we do not have any mf because there is a force mf here, but it's, but that is the point I'm checking the moment at. So it would, the mf force is not applying any moment about its own point. So this equation only has Ra, and you can solve Ra from here directly, and Ra is coming this, and then you can put this in this equation and get the Rf. So we have the reaction forces. And something, just note that I have taken my moment. Suppose I have taken the moment about F. So the moment applied by this force here is anti-clockwise. But suppose someone else is solving the problem and they take the moment about, conserve the moment about A, which will also get the same answer. But if you are doing sigma ma equal to 0, then look at this force. This force is applying a moment like this about A, and this is clockwise. So basically, the sense of a, even for a same force, the sense of the moment applied depends on the point about which we are considering the moment. So we generally, when we are solving the support reaction, this is of course a very simple problem, but if you have a fixed support, there will be two forces. I mean, the more complicated the problem is, the more number of forces that are at one point, I would prefer to take moment about that point and conserve it, so that the number of variables in this equation reduce. Since we took the moment about, okay, suppose I took the moment about this point mb, then I will have both Ra and Rf in the equation, right? There won't be a problem, because you will have two equations in Ra and Rf, and you can solve them simultaneously. But to make things easier, we take the moment about an already unknown force, so that in this equation we just have one unknown and we can solve it quickly. These things matter more in the competitive exams, when you have to solve the problems quickly, because in subjective exams you generally have enough time to solve. Now, step 2 is, take a section XX at distance x from the left support or right support, and solve for equilibrium in transverse force. Now, so one way of solve the reaction forces, we have to find the shear force pattern along this line. So we are going to take one, like a general section here. Suppose there is an XX here at a distance x from this support. Okay, where I find that with this 6. Okay, so basically, when we have a uniformly distributed force, well, this, the uniformly distributed force load, when we are taking the moment about some point, you can take this, the uniformly distributed load. It, see, this is expressed in kilonewton per meter, and you know the length over which it acts, so you know the total force, which is 12 kilonewton here. And to take the moment about any point, we can, it is statically equivalent to take the force lumped at the midpoint of this application area. So CD is this. This is a uniformly distributed load over the region CD. I can equivalently replace a uniformly distributed load with its magnitude lumped at the midpoint. Like this is a point load. This is a point load. Imagine this was also a point load of 12 kilonewton at the midpoint of C and D. So CD is 4 meter. So the midpoint will be 2 meter each from C and D. So the 6 that we get is 1 meter plus 3 meter. This is 4. DF is 4, and the midpoint of this application is 2 meter from D. So we add 2 here. This is where I'm assuming the point, the load to be lumped as a point load. Okay. So do you get it? Is that clear? Is that fine?
Yes, ma'am, it's fine.
Okay. So now the next step is us solving the. It should be 12 into 6. Yes, yes, it is 12 into 6. 12 is the magnitude of the load, that is the uniformly distributed load in terms of kilonewton meter, multiplied by the length over which it is being applied. So that is the magnitude, total magnitude of the force, and it is assumed to be lumped at the midpoint. That is what is here, 12 into 6. We take a section XX. So now the now, as I said, all the when we take a section, we are concerned about the sections in each, like between each two special points. So A and B are significant points. A has a support reaction, B has a point load. So whatever equation of bending moment I'll get within AB, it will be of the same nature. So I have to take one section in this AB portion. Then when I go into this BC zone, I have to take another section. So like we have to keep solving it. I'll show it with the example. In portion AB, look at here, look at this, look at just assume there is a section here that is distance x from A. X is a variable here. X ranges from 0 to 3 because I'm only looking at this zone, the AB zone. So x goes from 0 to 3. And now the shear force at this point, since RA I have already found to be 10.58, we now what we do for bending moment and shear force is we walk from one end. Like imagine you are walking from A towards B and you stop at a point XX. You stop at a point X from A. So what is the force? Just if I'm walking from the left side, just look at the forces that I've encountered on my left when I have been walking. So I have encountered one RA in the upward direction, that is 10.58, and then that is the shear force. So 10.58 is the shear force at any point I'm encountering in this zone, because wherever I'm stopping between when I have crossed A and I have not yet reached B, I have only one transverse force, which is 10.58 or RA. And that is the shear force in the zone AB. And for the sign convention, let's go back to the sign convention. This is a sign convention. So if I'm working from the left side and I have an upward force, I'm going to call it a positive shear force. So the shear force at in the zone AB is plus 10.58, and this is a constant in between A and B. So now SB just to the left of B. Now when you have a point load, you will have different shear forces at just to the left and just to the right. So when you are walking, you have reached B, but you have not yet crossed B. So you are just to the left of B and you have not yet accounted for the 5 kilonewton. So this will be just to the left of B, the shear force will be plus 10.58. Now I have crossed B. Now that I have crossed B, what happens is I have since I have crossed B, I am at a point somewhere here. So when you have walked from this side, you have encountered an upward force of 10.58. Then you have encountered a downward force of 5. So what am I left with? I am left with 10.58 minus 5, 5.58 kilonewton. Again in the positive direction, because I have walked from the left and I have ended up with a positive shear force so far. So SB just to the right of B is 5.58. So you see there is a jump SB. So at in the shear force diagram, at B just to the left I have 10.58, just to the right I have 5.58. So there will be a jump in the shear force diagram, and that is what I said in the beginning. There is a jump in the shear force diagram whenever there is a point load. So and now I have reached C, and I still have 5.58 kilonewton. Now this zone, now this zone is tricky because it has a uniformly distributed load, not as simple as a simple jump. So I'm somewhere here. Look, I am somewhere. Suppose I am somewhere here, that is at a distance x from this point A. So what happens? You are writing an equation. Sx is Ra. It is in the positive direction. Minus 5. Minus, now if I have reached here, which is at a distance x from A, how much of this load have I encountered? I have encountered this part, there was no uniformly distributed load. So this 4 meter is useless to me, but the total length is x. X minus 4 is the amount of uniformly distributed load I have encountered so far. And the intensity is W, that is 3 kilonewton per meter. So what Sx is Ra minus 5 minus W into x minus 4. So this is an equation. So Sx in this zone where x ranges from 4 to 8, because 4 x is 4 at C and x is 8 at D. It has a, the shear force diagram will have a linear profile, and if I put x equal to 4, I will get 5.58. So SC just to the right of C is 5.58, and now go to D. For D, I will put x equal to 8 meter, right? If I put it here, I'll get minus 6.42. So, okay, I'll go to the diagram so that you can understand right now how we show. So, see, so 10.58 is constant here. Then there is a jump downwards and I get 5.58. And then it linearly reduces. Like linearly, the shear force goes into negative. So, at C, I found out 5.8. At D, I find out minus 6.42. So, I join it by a straight line. So up to now we have gone to point D. Now portion point D. So now we move on to this portion DE. There will be no change here, because see at D, up to D, I am walking from the left side. So by the time I've reached D, I have accounted for all the forces before D. So in the zone DE there is no other force. So the shear force will again remain constant. It will, since I know that at D I have found out minus 6.42, it remains minus 6.42 up to A E. So just to the left of E, I know it remains constant. So again here 6.42, it is constant at E. Then at E I have a point load, so there will again be a jump. In portion EF, what happens is there was up to just to the left of E, I had minus 6.42. Now I have a jump of 10 kilonewton, and this is again minus. It is going to get added up, because I know when I'm coming from the left side, downwards is negative and upwards is positive. So minus 6.42 minus 10. So just to the right of E, it is minus 16.42. And again in the zone EF, there is no change, no force, so it will remain constant up to the end. So this diagram, so this is the final diagram, the shear force diagram. So see, at A there is a jump upwards. Why is it upwards? Because I am looking at from the left side and the reaction is in the upward direction. So there is a jump at A 10.58. Then in A to B I have no force, so the shear force diagram remains constant. There is a jump in the downward direction of 5 kilonewtons. So there is a jump here. It reduces to 5.58. Then it again remains constant up to C. Then since there is a uniformly distributed load, it reduces linearly. And why is it linear? Because the equation that we got, it was linear in x. The x was a 1 degree, x minus 4, there was a term x minus 4 there. So if you plot that equation, you will get this. But the easier way is just look at the shear force at this point C, look at the force at this point D, and join them by a straight line. Is there any question? Okay, so we to draw the shear force diagram, if we have a uniformly distributed load, if we find out the shear force at C and at D, and we just join it by a straight line. If it is a uniformly distributed load, why do I call it uniform? Because this intensity is constant, 3 kilonewton per meter, so it is uniformly distributed over this region. It will always be joined by a straight line. So when you are drawing the shear force diagram, you don't actually have to find out the equation. You can just find out the shear forces at both these ends and join the 2 points. Then DE, there is no force in this zone, so it is again a constant. Then I encounter a downward force of 10 kilonewtons, so there is a jump in the downward direction, and it becomes minus 16.42 and remains constant up to the end. And just look at it from the right side. Okay, since when you are drawing a shear force diagram, whether you come from the right side or the left side, it is not going to make a difference. So look at, suppose I am walking from the right side, I immediately encounter an RF. When we solved, it was RF was 16.42. So just forget whatever we have done up to now. Suppose we have just solved this support reactions, and I'm approaching the problem from the right. I encountered an upward force of RF, which is 16.42. Now again I'm going to go back to the sign convention. So in shear force, if I'm coming from the right side, downward force is positive and upward force is negative. So RF was a positive force, like it was in the upward direction, right? 16.42. So in the shear force diagram, it will go as negative. So when immediately I have a negative 16.42. Then FEI work, there is no force here, it goes constant. Then there is a downward force of 10 kilonewton, but since I'm coming from the right side, downwards is positive, so it has an upward jump of 10 kilonewton. Then it will again remain constant. And similarly, so what I'm saying is the sign convention is made like this because so that whether I'm approaching from this side or that side, we are going to end up with the same diagram. So the shear force, this was the shear force diagram. Now I'm going to look at the bending moment diagram. Again, we are going to, the approach is the same. We have to take a section xx at a distance x from left support or right support and solve for equilibrium and bending moment. Portion AB, suppose I am at a distance x from A. So what will be the bending moment at that point? It will be RA into x. Since this, suppose I'm here, this is x. So just as we saw while solving the equilibrium equation, we know that we have to if I have a point about which I'm considering the moment for a force, we need the distance, the perpendicular distance between the line of application of the force, which is RA here in the upward direction, and the point. So at this point, the bending moment will be RA into X. This is 10.58 into X. And why is this? And the sign, again, I'm going by the sign convention because this is really important. So when we are looking from the left side, clockwise moment is positive, anti-clockwise moment is negative. So you can see here that if this is my point about which I'm considering the moment for RA is providing a clockwise moment about it. So it will be, and I'm coming from the left side, so it is a positive bending moment. 10.58 into X. Again, you can see this is a linear profile, right? X will go from 0 to 3. At A, the bending moment is 0. And at B, the bending moment is 10.58 into 3, that is 31.74. And just note immediately here, MA is 0 because the rotation is completely free here. For a hinge support provides no restriction to rotation. That is why it has no reactive moment. So as I said, at any point the reaction, the reaction will be known or the response will be known. So here, since I do not know how much it will rotate, the moment is known to us, it will be 0. Now we move on to the next portion, BC. I have a section X from A. Now at this point, I have encountered two forces. So RA into X in the clockwise direction minus F into X minus 3, right? Because this force is applied along this line, and I have a point here which is at X from A. So it is at X minus, so this distance from B will be X minus 3, and minus because you can see it is in the anti-clockwise sense. So RA into X minus 5 into X minus 3. This is my equation. So MB, you will put, if you put 3 here, you will find you will come up with the same point. Okay, so there can be no jump in a bending moment diagram unless there is a concentrated moment applied at any point. So there is no concentrated moment applied at any point here, so there will be no jump. I got an equation for AB portion, and I got a equation for the BC portion. But if I put x equal to 3, I'll get the same value from both sides. So here we have got 31.74 at B, and at C I will put x equal to 4, and I have got something different here. Then I'll move on to the portion CD. Again CD is quite more tricky than the other ones because it has a distributed load. So I am at a point that is at x distance from A. So RA into X, it will be in the positive direction. 5 into x minus 3, it will be in the negative direction. And now I have a uniformly distributed force like this. So firstly it will be negative because it is in the downward direction, and I've come from this side. It is whatever the point here, wherever the point here is, the force, it is in the negative, in the downward direction, so it is providing an anti-clockwise moment. So the minus sign we understand. Now what we do is, this is 4 meter. So this 4 meter is not relevant here anymore. So if I am at a distance here, x minus 4 is the amount of uniformly distributed load we have encountered so far. So if I want to take the moment of this this part about a point here, what I said is we are going to take the amount, the force, the magnitude of the force lumped at its midpoint. Now here, earlier when we did, we considered the entire CD portion, so we considered the 12 kilonewton lumped at this midpoint. But I have only gone up to, suppose 2 meter here. Suppose my x is 6 meters, so this means I'm somewhere here. So the left, so the right portion, this part I have not encountered yet, forget about it. I am just concerned about the force to the left of my x point. So I'm going to take the magnitude of this force and I'm going to take it lumped at the midpoint of this region. So it will be, the force will be at here. So what it comes is that W into x minus 4. Firstly, x is the total distance. 4, this 4 is not relevant to us. So W into x minus 4 is the magnitude of force I have encountered so far. And I am taking it lumped at the midpoint of that x minus 4. So this is x minus 4, and the distance of my midpoint from the point I'm considering it about is x minus 4 by 2. So what comes is W into x minus 4 whole square by 2. So this is a parabolic equation. So when there is a uniformly distributed load, the bending moment diagram is a 2-degree equation. So this is the equation I'm coming up with, the parabolic equation. I put x equal to 4 and I'll get the same as this MC. I'll put x equal to 8 and I'm getting something different, and it will not be joined by a straight line. So let's see. This is a straight line, this I can join, this again I can join, but up to this will be a parabola. And see, the now basically the nature of the parabola could be like this, or it could also be like this, like concave and convex both. But from the more you can of course put, and you can put the values here at, so basically x goes from 4 to 8 in this zone, and I'm getting a parabola here. You could find out a few moments at this point. This one you could put x equal to 6, x equal to 6.5, 6.7, 7.5 and all that, and find the nature. But once you have solved a certain amount of problems, you will know that the nature will be like this. Anyway, for now, when you are beginning to draw this parabola, I would say you know the MC, you know the MD, and you should also solve the bending moment at 2 3 points in the middle, putting it in this equation. This equation, x equal to 5, x equal to 6, x equal to 7. Suppose you put these 3 points, and you will get three values, and you will join them, and you will understand the nature of the parabola, that it is convex. Okay, and then the next portion DE again. I have M. I have, now I am somewhere here. So RA into X minus F into X minus 3, that is same. Now when I am at X, which has, I have crossed the point D, then I have encountered the entire uniformly distributed load. So again I go back to the earlier what we did. 12 is the total magnitude, 3 into 4, and it is lumped at this point, at the midpoint. So the this force 12 kilonewton is lumped at the midpoint. So if I'm here, this is the distance I'm concerned about. It is x minus 4 minus 4 by 2. So if you if you look from, if you see here, this total is x. I subtract the 3, I subtract the 1, and I subtract half of this 4. So then I'll be left with the lever arm I'm actually concerned about. So it will be x minus 6. And now here again I get an equation, 10.58x minus 5 into x minus 3 minus 12 into x minus 6, and this is where x ranges from 8 to 11. So I have MD, which will again be the same as this MD, and I have ME, 16.38. So I'll join it by a straight line. So note one thing, that when we are looking at a shear force diagram in a zone where there is no concentrated force, it will be constant, and at regions of concentrated load, point load, there will be jumps, and in zones of uniform distributed load, it will be linearly distributed. The whole process is 1 degree higher in the case of bending moment. So in a zone where there is no applied load, the bending moment diagram is linear. at a point, and at a point where in a zone where there is uniform distributed load, the bending moment diagram is 2 degree, is parabolic, and there is a jump only if there is a concentrated moment, which are not very common. So there is no concentrated moment in this problem so far, so I can show that right now. Then we look at the last portion, EF. We take 10.58 into x minus 5 into x minus 3 minus 12 into x minus 6, and here again minus, because this is in the anti-clockwise sense, minus x minus 10 into x minus 11, because this length is 11, so the lever arm here will be x minus 11. And again I have an equation, and I'll put x equal to 11 and I'll put x equal to 12, and this is a check. MF has to be 0, because as I said, since in roller and hinge support the rotation is free, the reaction moment will be 0. So once you are done, you are coming from the left side, and once you have got the final profile, the last moment that you get at this point should be 0. If it is not 0, you have done something wrong, so go back again. And again, if I do the same problem from the right side, I will get the same pattern, and at MA the moment should be 0. So okay, this is another thing. Maximum bending moment. When it is a straight line, it is very easy to see where the maximum is happening. When it is a parabola, the maximum moment, to get that, we know that if, see this, in this zone, this is a parabolic zone. Mx is this. So to know at which x m is maximum, we know that the derivative should be 0. So dm dx equal to 0. So here, if you differentiate this, you will get a differentiate this and equate this to 0, you will get an x value. At that x, the bending moment will maximum, so we will find it is somewhere here. This is the maximum. And another thing is that shear force is basically the derivative of the moment, bending moment. Okay, so s shear force is dm dx. So at any point where the bending moment is maximum, the shear force is 0, so it changes sign. So here you will see that the shear force changed sign here. It was a positive at C and was negative at D, and to join it I had to change the point, and this will be the point where the bending moment here will be maximum. Since shear force is derivative of moment and maximum moment will occur where dm dx is 0, that means shear force is 0. And here I solved that I solved that equation. So if you take the derivative, you will find this equation. And let's see, at CD. At CD, this was the equation, 10.58 minus 5 minus 3 into x minus 4. And so if you take the moment derivative here, the derivative of the moment here, you end up with the same equation. If you differentiate this, you will see you will get exactly the same as that CD, the shear force in CD. So we equate this to 0 and solve x, and we'll get 5.86. So at somewhere here, the shear force changes sign and the bending moment reaches its maximum. Okay, so are there any questions now? Okay, so I'll move on to the, okay. I'll just do this from the right side a bit, because here I have RF in the in the upward direction, and in this zone I have RF will apply an anti-clockwise moment about any point in EF zone. And let's go back to the sign convention. Bending moment, when when I'm approaching from the right, anti-clockwise moment is positive. When I was approaching from the left, clockwise was positive. When I'm approaching from the right, anti-clockwise is positive. So since this is providing an anti-clockwise moment about this any point here, this RF, so the RF into X will be positive. So you'll see it is going positive. Then again it will be a straight line, then the parabola straight, and it will end at 0 at both the hinged and roller supports. And I would suggest that when you are when you are doing the first few problems, try to solve both from both ends, just to see that the nature comes exactly the same, and especially to make the concept of sign convention clear, because it is not as intuitive as in other cases we have encountered so far. This is another problem, and this is not a uniformly distributed load. When it looks like a uniformly distributed load, all these arrows will be of same length, okay? And if the length of the arrows are increasing, it means that the intensity is also changing. The not only is the force distributed, the intensity is also changing. So here if it is 1 kilonewton per meter, here it is 2 kilonewton per meter, like it is increasing and then decreasing here again. This first step remains the same. We have to solve the reaction forces. So now W per run per unit means at this point it is W kilonewton per meter, and at this point it is 0 kilonewton per meter. So it is a triangle by symmetry. We can, so now one thing is very, like a very important shortcut, that if a structure is symmetrical, if the loading and the boundary conditions are symmetrical, the reaction forces will be equal at both ends. And why am I calling the boundary conditions identical here? This is a hinge support and this is a roller support. But what is the difference between a hinge support and roller support? The horizontal reaction that the hinge support gives and the roller doesn't give. But since this is a beam problem where in the x direction there is anywhere nothing, so all the hinge support does is provide a vertical reaction, and the roller support also provides a vertical reaction. So for a beam problem, RA and RB are identical. They are the same boundary condition. But if there was any axial force, they would be different boundary conditions. In that case, the symmetry won't work. So here the loading is symmetric, the boundary condition is symmetric. So I can say that RA will be equal to RB, and that will be, obviously that will be half the total force being applied on the beam. Now see, if you are to find out the total force applied by a non-uniformly distributed load, what we have to do is find the area of this triangle. The triangle is half into L into W. We know that that is the area of the area of the triangle is basically the total force being applied. So in uniformly distributed load, it would be a rectangle. In uniformly distributed load, if I had to show W kilonewton per meter over this entire region, I would show is as a rectangle. So the area of this will be W into L. That is what we were doing. And here, since it is a triangle, we have to find out the area of this triangle. So it is half into L into W, and RA will be equal to RB will be equal to half of this total downward loads. Both RA and RB will be WL by 4. Since the total downwards load is WL by 2, at both ends I have an upward reaction of WL by 4 each. Now I'm going to take a section XX at distance x from left support and solve for equilibrium and transverse force. So look at a section X here. I'm coming from the left side. First I see RA in the upward direction, which is positive because I'm coming from the left side. So RA will be positive, and then I'm encountering a downward load like this. So the force up to x will be half into x into the w coord, or the, what is it called, ordinate, right? The y coordinate is called the ordinate. So for the abscissa x, there will be a certain w ordinate here. So the area of the triangle up to x will be half into x into this, and this I'm going to find out by the law of the similarity of triangles. So this will be, if at L this is w, at x this will be x by L into w. So look at this, Sx is Ra is WL by 4 minus the w x square by L. Now at x equal to 0, I will get this WL by 4 at x equal to L by 2. So at this point I'm getting Sc equal to 0, and so Sx will be 0 when x equal to L by 2, and then structure will not remain symmetric if there was applied horizontal load. So let us look at the diagram first. And now when when the load was uniformly distributed, that is in the form of a rectangle, the shear force diagram would be joined by a straight line. But here it is, since the loading is 1 degree higher, the shear force diagram will be 1 degree further higher. So it will be a parabolic equation. So here I know WL by 4, here I know 0, and if you go from this direction, and from this direction here you will see, if I'm going from the right direction, I come encounter a force in the upward direction, WL by 4. So it will be minus in the shear force diagram. So this point will be minus WL by 4, and you join it by parabolas. So this is the shear force diagram. And to get the bending moment diagram, I'll take a section XX, again like we do. So MX is RA. So I'm here, right? So due to RA, my moment will be in the clockwise direction, RA into X, that is positive. And now the moment due to this distributed load Now what we do in the case of moment is we find out the magnitude of the moment, and in uniformly distributed load we found out the total magnitude of the moment, and we lumped it at the midpoint. But for a triangle, so the midpoint, why it was a midpoint is basically in a rectangular loading pattern, the centroid is at the midpoint. But if the loading pattern is triangular, the centroid of the triangle is, we know, two-third from the like two-third from this vertex and one-third from the base. So if this is the amount of loading I'm considering, first I have to find the magnitude of the load, that is half into x into this ordinate, and then I have to take this force, that magnitude of force, lumped at the centroid of this triangle. So it will be somewhere here, which is at a distance x by 3 from here and 2x by 3 from A. So this is the lever arm. So wx square by 2l is the magnitude, and x by 3 is the distance of the centroid of this triangle from this point I am considering the moment about. So mx is wl by 4 into x minus wx cube by 6l. This is cubic. And you can find out, you will put x equal to 0. You'll find the reaction equal to 0 because it is a hinge support, and it is free to rotate. And at MC I find wl square by 8 for by 12. So since the loading is symmetrical, the BMD will be symmetrical about the center. So this is my bending moment diagram. This point wl square by 8, wl square by 12. I keep saying 8 because if it is a uniformly distributed loading of a supported beam, the midpoint bending moment is wl square by 8. So you can try that out. You'll mostly find it in any standard book. Now again look at this. So what we saw is, here the loading was of 1 degree. It was linear. The shear force diagram was 2 degree, and the bending moment diagram was 3 degree. So that is what happens if the loading, shear force, and bending moment are of a higher order each. So when it was a uniformly distributed load, the loading was of 0 degree basically. So the shear force diagram was linear, a straight line of degree 1, and the bending moment diagram was a parabola of degree 2. Here everything is one order higher. So this loading is linear, shear force is a parabola, and this is a cubic polynomial. Now, if suppose the loading itself was a parabola, the loading itself was 2 degree, that is also possible to be solved. The principle won't change. The principle will remain that to find the total load, we will take the area of that parabola under consideration, and we have to, for taking moment, I have to take the force lumped at its centroid. Now, the centroid of a parabola is not easy to find out. We have to find it with integration. That won't be given right now. Maximum you will encounter a triangular loading like this. So, okay. Are there any questions in the previous in this? Okay, we'll look at the last example. Suppose this is a new element that we are encountering. This is a hinge. An internal hinge. What it does is, the moment at an internal hinge will be 0. So I'll go into it. So basically, look at this system. It has a fixed support. A fixed support will provide a vertical reaction and a moment reaction, and this is a roller support which will provide a vertical reaction. So the total number of reactions is 3, and the total number of equilibrium equations we have is 2. So this would be an indeterminate structure, but we have a hinge here, so the hinge basically provides an additional equation. So we have three equations and three unknowns, and we can solve it. To solve reaction forces, first I am going to equate the Fy, so the total forces in the vertical direction to be 0. I am assuming Ra and Rc to be in upward direction. So Ra plus Rc will be equal to, this is W per unit length, and this total length is 2 plus 2 plus 1a, so 5a. 5a into W is the downward load due to the uniformly distributed load, and there is a point load 2.5 wa here. So the total downward load is 7.5 wa. So the Ra plus Rc should be equal to this. Now note, internal hinge at B implies moment at B from either left side or right side will be 0. Here I'm taking from the right side. So what I do is, to get mb sigma mb equal to 0, we are taking only this side. So first I encounter I have rc, which is at a distance 2a from here, and it is in this anti-clockwise sense. So suppose I'm taking anti-clockwise as positive here. Rc into 2a. Now this load is in the downward direction. It will provide a clockwise moment about B. So 2.5 WA into 3A. That is the moment due to this. And now due to the uniformly distributed load, the total magnitude is W into 3A, because this length is 3. I'm only looking at the right side. Forget about the left side. When you are taking that extra equation about an internal hinge, you have to look at either side, either of the sides. I am looking from the right side, so forget about this part completely. So the uniformly distributed load is acting over a length of 3a, 2a plus 1a, and I have to take it lumped at this midpoint. So from B, it is at a distance of 1.5a. So W into 3a into 1.5a, and it is again negative because it is it is in the clockwise sense. So equating this to 0, I get RC is 6WA, and RA will put here and we'll get it as 1.5 WA. Since both are positive, it implies that I had assumed it to be in the upward direction, and since the results are positive, it means that I assumed the correct direction. So RA, here there is a 1.5 WA upward, here there is a 6 WA in the upward direction. Now I take a section as we do. I have to take section XX at each special zone. So each distinct zone, AB is a zone, BC is a zone, and CD is a zone. So I'll solve for equilibrium. And here I'm approaching from the right side. Okay. So DC, in DC, if I take X from the right support, the the shear force will be 2.5 WA. This will be plus, though it is in the downward direction, because in shear force convention, when we are coming from the right side, downwards is positive. So 2.5 WA, and since this is also downward and I have encountered X length of this W, so WX is the magnitude in the positive direction. It will be 2.5 WA plus W into X. So at D, X is 0, so the shear force is 2.5 WA itself. And at C, so just to the right of C, the X is A, so this is 3.5 WA. Then I go to the portion CA, and actually the internal hinge actually doesn't change the pattern of the, like, it doesn't cause a jump or anything. So the CA is taken as a same zone. So suppose it is at distance X, what we get from the right side is plus 2.5 WA and plus WX, because uh, this is X from D, so W into X in plus, because it is downward direction, and RC I got 6 WA in the upward direction, so this is minus 6 WA, and this is the equation that we get in this zone. So X is ranges from A to 5A, because I'm coming from the right side, so at C X is A, and at A X is 5A. So at we'll see that when we put X equal to A, just to the left of C, we'll find minus 2.5 WA. So there has been a jump here. See, there will be a jump in the downward direction because there is a positive upward direction force here. And at uh, X equal to 5A, I have this value. So let's see the diagram. So what happens here is, there is a straight away, there is a jump because there is a concentrated load here. Then the unit, since it is a uniformly distributed load, the nature of the diagram entirely will be a straight line. So I join this by a straight line to this point. C, just to the right of C, I had 3.5A. Then there is a jump in the downward direction of magnitude C. There is a magnitude, there is a jump in the here F magnitude RC 6 WA in the downward direction, in the negative direction, since this force was upward and we are coming from the right side. So here there is a jump, and then again here I have plus 1.5 WA. So I just join this by a straight line, and this is the shear force diagram. And to get the bending moment diagram, we have to, again I am approaching from the right side. at at CDC, I have 2.5 WA into X, that is minus, because it is in the clockwise sense, and when we are coming from the right, anti-clockwise is positive. And similarly for this uniformly distributed load part also, it will be negative. It will be WX square by 2, because W Wx is the magnitude of the load, and it is taken lumped at x by 2 from this point. So this is a parabola. I again put x equal to 0 and x equal to a to find the two magnitudes. Then I come to this. And this is basically the same thing. I have to take the component, the moment for this minus 2.5 wax, then wx squared by 2, and due to this I will take magnitude of rc into x by a, and this is positive because rc is providing an anticlockwise moment. So I get here two values, and again, since this is a parabola, this is, since see this comes like this, and since this is a parabola, there will be some kind of like a maximum here, and to get that, what we do is dm dx equal to 0. So if we do, we have this equation. If we put, if we take the derivative and put it 0, we'll find that at a certain x the magnitude will be positive, magnitude will be maximum, and we get this here at x equal to 3.5 a, we get it at point 1 point 125 w square. So what happens is, here the moment is negative, here the moment is negative, but for a brief zone it actually reaches the positive part. So see, to sketch this diagram, you cannot actually, like, if you didn't find out this and I told you to join these by a parabola, you'll probably do it like this, you will probably keep the entire thing as negative. So to sketch the bending moment diagram, it is always recommended that just solve this bending moment at 2 3 points, and definitely at the point where it will be maximum. So first thing you do is put dm dx equal to 0 and find out the x where it is maximum and find out its magnitude. From that you will get a fair idea, and it is advisable that you solve at 1 2 other points to see the nature. And bending moment here is 0. So there are 2 points of contraflexion, and there are d1 and d2. So points of contraflexion are where the bending moment is 0. You can get that from the diagram. So this is the bending moment diagram and the shear force diagram, and they are both parabolic. This is parabolic and this is straight line because the force is a uniform loading. So the shear force diagram is linear and the bending moment diagram is parabolic. So that's this mostly covers the all the variety of bending moment and shear force questions you might have. So are there any questions?
Ma'am, if it have any movement at the mid portion of the beam, then how can we solve it?
Okay, so if there is a concentrated moment at any point, so what you will do is you are going to approach it in the same way. You are going to solve the reaction forces, and for the moment, suppose for the bending moment diagram, suppose there is a concentrated moment at this point. Okay, so you will firstly name that point something, and you will take the sections xx that we are taking at each of these zones, we will treat that as a special point. So okay, suppose there was not a hinge here, there was there was a consonant moment here. So I will take dc in the same way, then cb I'm going to take in the same way, and then when I come to b, I know there will be a jump in the bending moment diagram. Just like if there is a point load, there will be a jump in the shear force diagram, there will be a jump in the bending moment diagram, and I will have the direction, right? Suppose it is in the clockwise direction. So when I'm coming from the right side, clockwise is clockwise is uh, negative, right? So there will be a negative jump in the bending moment diagram of the magnitude of this moment. Suppose there is a magnitude of 5 kilonewton here. So this is my, so see, since it is an internal hinge, the moment here is 0. But suppose, okay, suppose here there was a concentrated moment, this point, okay. So at this point, there will be a negative jump. At this point, there will be a negative jump in this diagram equal to the magnitude of the applied moment. Do you get it? And then you will just continue with the equations again. After this point, you will again find out the equations and continue joining it with a parabola. Like here, there is a jump. Here, there will be a jump in the bending moment diagram. Is that okay?
Yes, ma'am.
Okay. Any other question? Okay, if there is no question, I'll end the class here today. We'll meet again next Tuesday.
Thank you.
Okay. Thank you. You may leave. I'll wait for 5 minutes to see if there are any other questions.